Testing, testing. Did it work? I don't know. I can't tell. I don't either. Pardon? Testing, 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 testing. Cool. What's your number? My wife wants to bitch at you if there's a problem with the stream.
It's 901.
901-230-0957. 0597. There's spares of everything and extra stuff out here.
Can you relatively to it?
I don't know.
I don't see it on the
YouTube channel. Yeah, we might just need to record it and pass it along.
Yeah, I mean, it's recording.
Maybe. I have no clue.
Streaming live, YouTube, PGSA.
Weird.
Yeah. I don't know.
I don't
I
either.
don't see it on here, so this is going to be live streams. That was from some weird day.
Yeah, oh well. Don't stress too much, Anthony. Yeah.
The quality of our questions depends.
Is that a good thing or a bad thing?
Depend on.
And Anthony brought the coffee, so
Yeah, it's all decaf.
I don't drink coffee, so I don't know.
All bean,
Yeah, I should.
which I think is perhaps vacuously true.
Yes, it is. Unless you put milk in it.
True, yeah.
Or get. Well, he's probably back on the train.
What?
He's probably back on the train. Huh? We can't. If he's underground, he doesn't have service. I won't argue with you.
No, I know. I'll be asking too many questions. So, let's start. It's my pleasure to Sorry.
I'm done.
Yes. Brendan Frost, he joined us 4 years ago, right? Yes, and he started in a group of then Brendan switched to Dr. Nicholas Ditt's group. Sadly, Nicholas, the group got transferred to been working together since then. There you go.
Thank you very much for the introduction. Thank you very much to my committee for being here. I appreciate your time. Hopefully it's not wasted. So today we're going to be talking about the optoelectronic and transport properties of group 3 nitrides. So to start off with, not many of you have seen group 3 nitrides. I haven't really seen group 3 nitrides. Actually, before that, this is the work I did before I joined Nicholas. So I did some work with viruses. Probably a lot of you heard me complaining about that. And I did some work on VO2, vanadium dioxide, some interesting metal transitions there as you change temperature of that. And then I was also part of a presentation that Indica gave doing work studying the indium nitride that was produced in this lab prior to actually joining this lab. What I'm going to talk about, group 3 nitrides, why are we actually studying them? What do I care about them? I'm going to continue on talking about simulation of infrared spectra, how this ties into group 3 nitrides, why I care about that. Going on to talk about the high temperature growth of indium nitride, and then on to what I plan to do and the conclusions for this talk. Starting with group 3 nitrides. So now, this is the picture of group 3 nitrides that I was talking about. Group 3 nitrides are these brownish, greenish, colorblind materials. So this is aluminum nitride, this is gallium nitride, and this is indium nitride on a sapphire wafer. And this is the only one that I've actually ever seen in real life. What I end up looking at most of the time are these. This is the materials through the eyes of a scientist, through the eyes of my machines that I work with every day. We have visible spectroscopy, we have atomic force microscopy, we have Raman spectroscopy, and we have temperature-dependent resistivity. All of these measurements are taken of our samples, and this is the data that I look at, and this is how I describe these materials. Thankfully, it does not rely on color. So, why do we care about these materials? Well, when we're talking about these materials, we're talking about advanced electronics. Electronics we usually deal with today are silicon-based. We are starting to branch off into the nitrides. They have made LEDs from nanorods for the indium gallium nitride. They have made high-energy transistors with gallium nitride going up to 600 volts, 220 amps. They also have made, and I couldn't find a nice picture of this that I could guarantee was nitrides, but solar cells. They're working on making higher efficiency solar cells with these materials, which we care about because they fall in the same system and have a very similar lattice structure with a large range in band gap. So we have, starting down here at indium nitride that I work with, 0.6, 0.7 EV as a band gap, going all the way up to about 6.1 within the same material system. So we have indium nitride, gallium nitride, and aluminum nitride that all have a very similar lattice constant, which is the size of the crystal, with a very large variation in the energy band gap. So we can start thinking about these materials to make sensors that are variable from infrared all the way up to UV. This is a huge thing if we can get it working properly. So, what are group 3 nitrides? Group 3 nitrides are a wurtzite crystal in their base form. Going back here, this is for the wurtzite structure. There also says zinc blend structure, which can be made, but it's metastable, so we don't want to bother with that yet. Anyway, so this is the wurtzite structure. We have aluminum, gallium, or indium. Up here is the blue or purple. And then we have the yellows here as the nitrogens. It's a shifted hexagonal lattice structure. So we have 2 hexagonal patterns, one shifted over from the other, and they lay like this with layers A, B, all the way up. When we look at the reciprocal lattice for that, it still forms a hexagon structure. And this is the reciprocal lattice, yeah. So these are the points that we care about here. This is the gamma point, which is the center of the structure, and that is the foundation for the band gap. The band gap appears at that gamma point in reciprocal space. So when we look at the band gap structure, each of these are direct band gap materials. What that means is that the conduction band and the valence band are closest together at the same point in K-space. In this case, as I said, that gamma point. We can also see the band gap increasing as we go from indium nitride to gallium nitride to aluminum nitride. These are theoretical calculations done by Carvalho. How do we make these things? We make them with MOCVD and a variation of MOCVD called MEPA MOCVD. MOCVD stands for metal organic chemical vapor deposition. Basically, we combine the gases that are the precursors. So in this case, we have ammonia, and for this one, TMG, which is trimethyl gallium, into these 2 inlets here. They come into our reactor chamber, where there is flows which carry them from the top down. There is a heated base, you can see the heating element here, and a wafer carrier which contains our 3 wafers that we're growing the material on. And right above that wafer carrier, we get the chemical reactions that form the materials that we actually care about and we want to study. So here we have the ammonia coming in. We have TMG, the gallium with 3 methyl groups attached to it coming in. Right above the template, the wafer carrier or the templates, we have this area where there's high energy, high temperature, and the ammonia breaks down and the TMG breaks down, so we can combine the nitrogens and the galliums to make gallium nitride.
So what is the high temperature?
There is a heating element underneath,
So
in this case.
radiant heat.
Just radiant heat, yes. For MEP MOCVD, or Migration Enhanced Plasma Assisted MOCVD, we use a different method. Instead of having a high temperature here to get our nitrogen precursor, we use plasma. So we create a nitrogen plasma here, which is positively charged nitrogen nuclei, as well as electrons coming down. And they pass down and they combine at that surface, similarly with the gallium. So we still have a slightly high temperature where the gallium or the indium nitride can decompose at this point. This system is mostly used for indium nitride. But we have this high temperature region where the TMG or TMI can decompose, and they combine with the nitrogen ions from the plasma instead of from ammonia. And they can then form on the surface and grow the material on the surface. Once we've grown them, we need to characterize them. I don't actually grow them. We have Zahir and Mark standing outside there who do most of the work on those machines. And then I step out and I take that material and I say, guys, this is what you did. So the first thing I want to look at is I want to look at how thick is the material. So I place it underneath a fiber here. Those fibers connected up to a spectrometer and a light source that's hidden behind the computer. We shine light on this sample here. The light bounces onto the sample, reflects back up, and we collect it in the spectrometer. And we see thickness-dependent fringes. So basically, as we change the wavelength, the intensity of the reflected light increases and decreases, and we can correlate that to the thickness of the material. A nice thing about it, well, is where these fringes stop is where the band gap is. So we can actually directly measure the band gap of the material as well at the same time. Now, that being said, this is only from about 200 to 900 or 1,000 nanometers. Indium nitride has a band gap of 0.6 eV, so that's much lower energy. So that's all the way off on this side of the graph. So we can't actually measure the direct band gap of indium nitride using this machine. The second thing, or another thing that I work on, is the Raman characterization. We have a home-built Raman system here, which basically takes light, shines it in onto our sample. We focus it onto our sample. If you pay careful attention, there's actually no sample in this picture. And then the light bounces off of that sample, having gone through Stokes scattering, which is a inelastic scattering. That light comes back out. We filter out the green light because it's our laser. We don't really care about it. We just wanted to use it to do something. And we get out the information about the phonon structure. We see where the phonons are, and we see the energy difference between the laser coming in and that phonon. And that's what we were measuring here. And it gives us a clue as to how well defined our crystal structure is, as well as if there's any stress or strain in our crystal structure. Are we actually at the point where we usually measure this peak? If we're not, then the crystal is not in its usual position, its usual condition. And here's a brief schematic of that as well. Comes in, bounces out, comes down, comes back with a filter to block out the green, and we're left with the lower energy light coming to our detector. Now, the one thing with this system is that it needs to be calibrated. Since this is a home-built system, not a commercial system that we can say, okay, plug and play, let's do it, we can't assume that. So back in April of last year, we got some results back from a commercial system in Berlin with work done by Daniel. If you guys remember Daniel Seidlitz, he was one of the group members that we've worked with. And you can see that there was a visible difference for the same sample in the Raman peaks. So I spent about 3 or 4 months calibrating that Raman spectrometer to make sure that we got it right, and I did the best of my work. And a couple months later, I realized I needed to actually make sure that I was doing a good job, and I plotted the same results with the same sample again, and you can see with my calibration, we shifted them right over, and it worked. So this system is now calibrated, even if it wasn't back in April. That being said, the results that we usually take away from this are difference measurements. So even though a peak may be shifted, the difference between two positions on that peak do not vary significantly. So most of the measurements that we made with this system are not called into question. It's just a little bit more accurate now. Another set of measurements I make are resistivity measurements, transport measurements. I use a low temperature cryogenic system to lower the temperature of a sample as I measure the resistivity across it, as well as the Hall coefficients. I can also measure magnetoresistance this way as well. Use an atomic force microscope. Here you can see a couple images of gallium nitride. This is gallium nitride on gallium nitride. And this is gallium nitride on sapphire. You guys can see a little bit of a difference here. The difference is that sapphire does not have the same lattice constant as gallium nitride. So we need to make sort of a transition layer between sapphire and gallium nitride, and that leaves us with an imperfect surface. We can refine this, but at the end of the day, we want to get it to look like that. So where we have gallium nitride on a gallium nitride surface, you can see that this is only a range of 700 picometers over 10 microns. These samples are sitting at, okay, the thickness question is a bit of a challenge. This is pure gallium nitride from the bottom up. So the layer that we grew on top, is that what you're asking?
No, let me explain it.
Sure.
The layers, the overgrowth.
Yes. So the layer we grew, both of these layers are grown upon gallium nitride that is on top of the substrate. So this here is gallium nitride on gallium nitride. This one is gallium nitride on sapphire. So this one is about 1,100 nanometers of our gallium nitride grown on top of a gallium nitride substrate, which we purchased. This one is about 2,500 nanometers of gallium nitride that we grew, 1,100 and 1,400 at separate times.
Just relax.
It should be totally relaxed by this point, yes. Okay, and then the heart of my work, which I've enjoyed doing, is the Fourier transform infrared spectroscopy. We take a sample here, we put it into the FTIR spectrometer, which takes the light, bounces it here, and has a scanning mirror. So we can vary the intensity of the wavelength that is actually reaching the sample, and we measure that signal coming out. And that variation is a function of wavelengths. So we need to, as it says, take the Fourier transform of that in order to get our spectrum coming out of that. And again, this here provides us the information about the thickness. You recognize those thickness fringes, which is the same as the thickness fringes, although shifted up in wavelength, or shifted up in wavelength. But then we get to this section over here. And this section here is perhaps what's most interesting to me. And this is the phonon structure. This phonon structure here tells us about the material itself. So yes, we can get the thickness of what we've grown, or whichever layers we've grown. But when we come over to this section here now, we can actually start talking about what is the material we've grown? How is that material behaving? Is that material doing what we think it's actually doing? So we're going to transition to that part of our talk now. Can I simulate the reflectance that I get from the FTIR in order to talk about my crystal structure, in order to talk about the charges that I have moving around in my crystal structure? So the first thing we want to talk about, going back to this picture here, is what's going on here. In order to talk about this here, I need to talk about the dielectric function. If the dielectric function was more or less constant or smooth, I wouldn't see this here. I shouldn't say smooth, sorry. Smooth is not a good word. It's a mathematical word that means a lot more than I think it means. So this here, if it was well behaved and kind of flat like the rest of it, I would just have these reflectance fringes all the way across. But because it isn't, because I have these phonon frequencies here and this plasma frequency, that changes the entire way that my sample reflects light. That's what I'm looking at. So the dielectric function here, and there's actually two of these, one for the perpendicular polarization, one for the parallel polarization, has these terms here, LO and TO, omega LO, omega TO, which correspond to the longitudinal and transverse phonons. Now, if you look down here, most of you should know this, but there might be people who are watching who don't, are the shifts of the phonons from their actual position. So if this is where sorry, not the phonons, the shifts of the atoms or the molecules from their actual position. So if I have my atoms lined up in a row like this, where that dotted line is where they should be, a transverse phonon shifts them away from that line perpendicular to that line. A longitudinal phonon shifts them in the same direction as that line, but shifts them up and down so that they compress between them and increase the space between them. And all of this now, although it's nicely laid out in a 2D grid, is actually happening in my Wurtzite structure model. So we have atoms that are moving up and down like this. We have atoms that are moving in and out like that within my Wurtzite structure. And those are the phonon frequencies that I'm talking about. The gamma functions here are the damping coefficients for those phonon frequencies. And this is the damping for the plasma frequency. The plasma frequency comes out of the charges, the free charges that are able to move around within my structure. So I have electrons or holes that can move around, and that there gives me the information about that. So going back now, most of you have taken EM2 or EM1. Dr. Dietz would gladly go on and on about reflectance from a surface. So at our surface here, we have light coming in, and we can imagine this is the light from our spectrometer. It hits the top surface of our sample. Some of it will go through, some of it will bounce back, and at the end we'll have some coming out, and we'll have some potentially coming back, depending how many layers and what we're bouncing off at the end. To simplify our lives, we will assume that there is no light, there is no light coming back. So these D terms here are 0, and as you can see here, the paper that I've been working from, this should be B and not C. There's a nice typo there. So The way that we model this is with a matrix. So we can correlate the incoming and outgoing waves with the incoming and outgoing waves on the other end of the layer. This is called the transfer matrix. There's a nice elemental representation here. But we need to define that. So, some work done by Behrman and Schubert. If I have a transfer matrix for each layer, I'll need to multiply all of those transfer matrices together, combining that with an incoming and an outgoing term in order to define the reflectance from my model. This delta matrix here defines the behavior of that individual T matrix. And since it's very hard / impossible to take a exponential of a delta matrix, we need to expand it. It's basically a Taylor expansion of the exponential. And with these beta coefficients here, which depend on Q, which are the eigenvalues of that delta equation, delta matrix. So to define that delta matrix here, we use the dielectric tensor. So you saw how I defined the dielectric functions. Those dielectric functions are fed into this dielectric tensor down here. So going back to my structure, I should have put a structure picture here, but I have a structure which is hexagonal in this direction, and in this direction it's different. So in the x and y direction, the dielectric function is the same. However, in the z direction, my dielectric function is different. So to complicate matters even further, we assume that my crystal structure is not aligned vertically with my system structure. So if I take a look at my Fourier transform infrared spectrometer, I have a plane sitting like this where I put my sample, and this is up, but that may not be up for my crystal. And I know it's not up for my crystal because of the substrates that we bought. So we have a tilted axis, which is what these A functions do here. These A matrices will rotate my dielectric function so that my dielectric tensor now speaks to the actual dielectric tensor that the light is experiencing in the laboratory reference frame. That feeds back into here, and this K value is just the parallel, the component of my wave vector that's parallel to my surface. All of this feeds together to make some fits. So originally what I was doing was I was using a 2x2 method, which took just the parallel, I believe, if I have to remember correctly, the parallel components of my light. So I didn't bother with the perpendicular components of the polarization. And what that left us with is a couple of points where there was no good fit. So you can see here, I have a black line and a red line. We're talking about sapphire specifically. Here, there's a section where it deviates there, and there's a section where it deviates here, and corollary there. And the polarization. So I took it into account and I started working on it. And I got to this point here. I compensated for that and I compensated for that. Now I need to extend it to more than just one layer. So basically I just modeled the reflectance at a single surface of sapphire. What about gallium on top of sapphire? And when I did that, it didn't work. So this is what I'm continuing to work on. It turns out there were some problems with the model I was working with. So I'm going to extend that model a little bit and try and get this to work. That's my continuation. I'm also going to work on getting the roughness modeled. If you didn't see any roughness terms up until this point, Nevo and Crochet defined a model back in the 80s, but you can see it's defined for this model here where this is the ratio of B and A. Again, not C, B. And this works very well when I have these terms exactly, but now I need to incorporate that into a 4x4 matrix method where there may be differences in the directional components of my dielectric function as well, which affects these K vector values. So that's what I'm going to be working on as well.
Can you relate that?
So long wavelengths here, I think these are actually the long wavelengths here. At the short wavelengths, it seems to work pretty well. Yeah, reciprocal space, sorry. Yes. So here it's working pretty well because we're not very rough. I'm going to put it bluntly. We don't have a particularly rough surface at this point, which is great for gallium nitride, but for indium nitride that is a problem, and we'll see that in a second. So the roughness is what I'm hoping to incorporate into this model as well. Going to do a bit of a transition here, talking about the high temperature growth of indium nitride. Now, the question that we want to ask ourselves is, why do I care about the high temperature growth of indium nitride? Why can't I just grow it at low temperature? Well, it goes back to the gallium nitride. Materials are well defined, well studied. They work the way they are. And they're grown at 1100, 1200 degrees Celsius in MOCVD. There are other methods to grow them that have other temperatures and other pressure regimes that they work in. But when I look at indium nitride basically breaks down way before I get to those temperatures. This is a study done at atmospheric pressure, so it is a little bit different, but from most of the reading I've done, getting it to work above 650 degrees Celsius doesn't happen. The decay rate is much faster than the growth rate. Growth rate is a big problem as well because commercially, indium nitride is not a viable system yet. We cannot grow it fast enough to make it commercially viable so that we can make devices out of it at a large scale. So, how do we do that? Well, if we come back here, the graph I had at the beginning here, if we set this at 1000 degrees Celsius to grow our gallium nitride, I can't put indium into the system. It will decay, it'll evaporate, it'll decompose before I get a chance to do anything with it. So what our lab has been working on is migration-enhanced plasma-assisted MOCVD, which starts breaking down at 650 degrees Celsius. We start using nitrogen ions from plasma. What this allows us to do is this allows us to work at a lower temperature, and it also changes the kinematics of the reaction at the surface, feeding more energy into the reaction at the surface, allowing the atoms to move more freely, allows them to find the right position to be in, grow the crystal structure. And we can show this. This is the system itself. So you can see here, this is our plasma source up there as well. We have the chamber, which goes out here. The plasma flows down, and our wafer surface is down there. You can see a nice glowing plasma right above our wafer surface. And this over here is the way we get our samples in and out, the load lock. So going to higher temperature, we actually do grow indium nitride. We take a look at the indium nitride. We tried growing it at 900 degrees Celsius, 875, 825, 775, and 675. All of these temperatures are above that 600 to 650 degrees Celsius. That's a decomposition temperature. Now, word to the wise, this is a very low growth rate. So that means that our growth rate is just slightly above the decomposition rate at this point. So we're only talking about 45 to 55 nanometers of material for these samples, which is part of the reason they're noisy in the Raman. But what that means is that we have indium nitride peaks showing up in our Raman system. So we have indium nitride on our surface. We model these indium nitride peaks, and we can correlate them to the phonon structure of the indium. We have the A1TO phonon, we have the E2 phonon here, and we actually have two peaks for the E2 phonon that we're talking about. There's the B1 phonon here, there's an A1 and an E1 LO phonons over here, so the longitudinal phonons. So this shows us that we have indium nitride, and it shows us that we have indium nitride all the way from 675 to 900 degrees Celsius on our growth surface. We've done it. Now, I'm going to preface this by saying it's been done before. Dr. Dietz did this with the high pressure MOCVD as well. But we have hope for this because it's a completely different reaction dynamic. So we're going to explore this a little bit further. We can see here the E2 broad and the E2 high peak. Going back here, we defined two peaks because it was modeled better by two peaks. And we have evidence that shows that. So if we look at the E2 high peak here, the E2 high peak decreases as we go to high temperature. That means that the crystal quality gets better. Yes?
You meant?
Yes, full width half max, sorry. And that is clearly labeled there, even if I got it wrong. So the full width half max of the peak decreases here. And what that means is that the crystal quality gets better as we go to higher temperature, which is nice. That's exciting. We want better crystal quality. But we still have a second E2 high peak that kind of does the opposite thing. So we need to understand that as well. We took this and we did the AFM measurements of the sample. So we put it underneath an atomic force microscope, and we actually measured the surface of the sample. And that measurement showed us what this indium nitride looked like. And you guys remember the gallium nitride from earlier? Nice and flat with those beautiful layers. This does not look like that. So as you can see here, at the lower temperatures, 675 and 775, we have a very granular mess. It is indium nitride. We have the Raman peak to show that it's indium nitride, but it doesn't look very nice. And I mean, it still doesn't look very nice out here either. But as we start getting out here, we start getting larger structures. And we believe these larger structures are what leads to that E2 high peak. So we have a larger crystal, which we can actually measure as a distinct material away from this granular background. So that's what we think. Now, during the process of doing this, we came across something else. As I was trying to scan the sample at 825, grown at 825 degrees Celsius, we got really, really ugly AFM measurements. A bit of a preface here. Do you guys know what AFM is? AFM is basically a record player, for lack of a better word. It takes a needle and it scans it across the surface. And the way that the tip interacts with that surface tells us what the surface looks like. When the tip interaction goes weird, then our surface picture starts looking weird. And that's what's happening over here. On the bottom here, you see what the surface should look like. This is what it says it looks like. On the top here, you see a measure of the tip interaction. This is the phase difference between the driving force for that tip as well as the measuring time for that tip. So you can see over here, there are a lot of points on my material where that interaction is not happening rapidly. There is a change in the time. The time difference between it being told to move and it actually moving is large here. And the time increase here is from me grounding it. So I took my sample out of my machine because I saw that it was doing this. I took my sample out of my machine and I grounded it. I took a wire, I literally soldered it to the top of the sample in order to ground it, get an electrical connection from the sample to the ground. And I let some time pass. So at T0, which at this point means absolutely nothing, it just means the first time I got it back into the machine after I soldered the wire onto it, it looked like this. As time went on, you can see that my phase changed. I actually changed something with the interaction between the sample and the tip to make a better AFM picture to cause less interaction with my sample. I'm positing that this is the surface charge accumulation layer. It is known that in indium nitride, there is a surface charge buildup. And what this buildup does is, if you have an AFM, it actually messes with the interaction between your tip sample and the surface of the material. The sample's charged. And I discharged it by grounding it.
Like devil's advocate.
Sure.
What kind of solder?
Indium. Pure indium, yes. Well, within some accuracy limit, yes. It is possible. That being said, I took the same sample and I disconnected it and I tried it again. And after some time, it actually showed me that again. I believe this was actually the second time I scanned it. So this is the second time it cleared out and then it redid it. And that is actually further evidenced by some of our transport measurements. I measured the resistivity of these samples, the entire temperature range, as I cooled it down and warmed it up. And you can see here that as the temperature changes, the resistivity changes. So starting at 675, I have a high resistivity for that sample grown at 675 degrees Celsius. Moving it up in temperature, I grew at 775. Well, I didn't, Zahir grew. These samples were grown. 675, 775, 875, 900, and then 825. And I still don't understand that. This is that same sample that we were having these problems with. So it seems for some reason there's a very large surface charge accumulation that plays into the resistivity of this sample being different from these. This is growth temperature, yes, sorry. This is not the temperature measured. This is the temperature scale of the measurement. So, yes, thank you very much. But the other thing that we need to pay attention to here is that this change is extremely small. So we're sitting at 0.674. This is a log scale. And the program I used to program it wouldn't even give me another set point on there unless I shrunk the data down so that I could actually see another point on the side here. So these measurements are actually very close together. So it is possible that any variation I see here is artifact. But there is a trend, and it is broken by that sample, which was demonstrated in AFM as well. So moving forward, talking about proposed work and my conclusions. What I want to do, I'm going to complete the modeling work of infrared reflectance. I think it's important to understand this material. It's important to be able to make measurements that we can make and actually understand what we're doing as far as the growth goes. I want to add interfacial roughness to the modeling. If I can make a more accurate model, I can use that accurate model to better understand the material so I can combine it to get more information about layer thickness and phonon structure. The better I make that thickness section, the better I make the information about my phonon structure. I can combine this Hall and resistivity data, which can lead to carrier concentrations, with the plasma frequency that I can obtain up in the IR reflectance, and I can use that to feed back to my phonon structure as well, and to my band structure, because I can find the effective mass of my carriers. I also can verify the resistivity results from high temperature growth and explore these results as a function of the growth parameters. So that's what I plan on doing going forward. Some conclusions. Infrared reflectance modeling can give me my free carrier concentration, effective mass and of the charge carrier, and or the charge carrier concentration. Those are not exclusive, unfortunately. I can find my phonon frequencies and phonon damping coefficients. I can find growth feedback for my interface perfection, interface transitions. Indium nitride, we can grow it at a temperature above the decomposition temperature. At higher temperatures, larger structures are observed, and that might be a clue to getting better indium nitride. High temperature indium nitride Raman is best modeled with 2 E2 phonon peaks, which gives us better information and leads to a better understanding of the larger structures that appear on the AFM. And there is a distinct possibility that surface charge is affecting the transport measurements for this entire series of runs because these samples are so thin. Sitting at 50 nanometers, we might not be getting a true measure of the sample's properties itself. With that, I'd like to thank Dr. Dietz. He's not with us, but he gave me a great opportunity to be part of this group. I'd like to thank Dr. Cosner for taking over. He definitely didn't have to, but it's been a pleasure working with him. I'd like to thank Mark and Zahir, without whom I would have nothing to study. Daniel and Indica, both former members of this group that I was privileged to work with. I'd like to thank Carola. Whenever I need something that we don't have in the lab, I go to Carola and say, hey, and she says, sure, most of the time. And then when Carola doesn't have it, I go to Pete and I say, please make it, and he says, no, and then he says yes. I'd also like to thank my wife and family. Their patience, yeah, couldn't do without it. Thank you very much for being here.
Now, let's open discussion. General public and committee members, could you please hold your questions till Torture can later? Questions?
Yes, Anthony.
Slide 18.
I numbered my slides.
That's very helpful. Yeah. No,
Lag. We'll call it lag.
So in this calibration procedure, so you shifted the peak to match the Berlin data. Is the difference in the widths of these distributions
Something to worry about?
something to worry about?
If they were,
It's a system
if they were the same system, yes.
Right. Yeah.
So the problem with this data, as far as our system versus Berlin system, is Berlin has a what's the word I'm looking for? It's a different type of Raman system.
Okay.
So they have better focus than we do. We have micro Raman, I believe. They have confocal Raman microscopy. So they have confocal Raman microscopy, which means that they have a much smaller focal volume than we do. So although we have a good focus in the XY space, we have a large focus in the Z space. And what that means is that we get information about a taller section of the material than they do. So we are looking at not just the surface, but we are also exciting further down into our materials. So we can get a larger distribution of values for the full width half max because there's more distributions of phonons affected by the light.
More advantageous in this higher wave number area? Is that why you can see that sound?
I would actually argue the opposite.
Oh, okay.
We do not really care about the sapphire peak. Yeah, it means nothing to us. It's just the substrate.
Okay.
The things that we do care about, though, talking about this higher area here, is this peak over here. This is actually AlGaN, so it's aluminum gallium nitride. And what that means is that this A1 peak is actually shifted for the top layer, this AlGaN layer on top of our gallium nitride. So this here, as long as we can see that, we're good, because that means we're seeing the top surface of our sample. Yes, I'm in.
So it seems
The roughness is a concern. I want to stop the roughness, if that makes sense. So when we're talking about indium nitride, and so AFM can give us a direct measurement of the roughness. That's great. But when I grow on this, how do I know how the growth changed? Do I know that the next molecule, the next atom that I put there went to the right position? Or did it start making a cluster? So instead of growing evenly across this entire surface, did I make a cluster now of indium nitride growing on my gallium nitride? Did I make a cluster here and a cluster here, and now they're growing separately and then merging later on? And when I get to my top surface might look like this, which is only a variation of 7, 8 nanometers, which is great. It's not terrible. It's not ideal, but it's not almost terrible, yeah. Oh, this is 10 microns, though. This is 10 microns, so it's not that bad. So yes, I do care about that interfacial roughness. That being said, when I look at my indium nitride right now, it's not even close to smooth. So yes, that is a major concern. That roughness needs to be fixed. We need to be able to grow indium nitride well before we can carry on with it and start making better devices out of this material. That being said, understanding the transitions between materials is what the FTI is. So yes, roughness is important to me. No, it's the main purpose of my study.
absorption.
So we're dealing.
We know that materials can reflect a specific.
So all of our materials are basically reflecting somewhat from most of the visible spectrum. 25%. So that's not bad. Pardon me. But when we talk at, you want to add something? Okay. When we go to the infrared, here we're sitting even lower, and then weird things start happening over here. So yes, there is transmission, there is reflectance, and there is absorption at all of these levels. But I guess what is your question about that?
Which kind of because you want to make a sensor.
Yes, and that depends on the sensor application. The better we get these materials, as I said, if we get the materials right, if we can actually have what's called tertiary semiconductors, so indium gallium nitride or indium aluminum nitride that are more indium rich than gallium rich, we can start moving all the way to the infrared. Right now, we're kind of stuck. We can't really go between 75% gallium nitride. So right now, indium 25, gallium 75 nitride. And at that point, we're starting to get into the visible, but we can't go lower than the visible. And all of these work if we can get it right if we can get indium nitride and InGaN all the way up to indium aluminum nitride, then we can cover the entire range from 0.64 eV, which is 5,000 nanometers, all the way down to 300, 250 nanometers with aluminum nitride. Well, I guess 350, somewhere there. So, did that answer your question? Okay. Yeah, Tranga. It depends on the material.
Okay, so then
Yes. Yes, that has been tackled by people smarter than me. I am doing the analysis at the end. So the growth is mostly handled by Mark and Zahir. And we've had discussions about it. That's part of the reason we're using sapphire. Sapphire is a material that has similar thermal coefficients as gallium nitride and neodymium nitride, so that they do expand and contract similarly at least. Yes.
Can you go to slide 30?
Yes.
Or actually, I think it was
30. Yes, you're right.
no, it wasn't. It was the one where you were fitting your
That one?
Yes, yeah.
Okay.
What is the difference left to the one on the right? How many terms do you have to add to?
So
The main question is, at what point do you think you've begun to overfit data?
the model that we're defining is based on the understood structure of the material. So from here to here, I believe we're adding effectively 4 terms, if I remember correctly. But each of those terms is based on the actual physical structure of the material.
Okay.
So for each of these curves here, that curve there and this curve here in the black, right here and right here, there is a phonon, which is not expressed in this model. So by expressing that phonon, because we're dealing with both polarizations and not just a single polarization of light, then I can actually fit those 2 terms.
Okay.
Grab snacks,
Let's paint this picture.
grab snacks before you head out. I don't want to take it down to 400.